Hi everyone, I just wanted to do another Faraday's problem, and the problem is this. A rectangular conducting loop of 20 turns copper wire is rotating about the z-axis at 6,000 rpm in a spatially uniform magnetic field given by B is equal to y hat 0.15 sine 20 t Tesla. And it's asking, what is the direction and magnitude of the induced current on the ring when the ring is on the xz plane at time is equal to 0. To find the direction clearly with a sketch, the resistivity of the wire is 0.1 ohms per centimeters. So just like any Faraday's problem, I'm just going to first start off with my flux, which is simply just going to be B dotted with A, or this will just simply be BA cosine some angle. And the question comes up as, what will our angle be? Well, in this case, it is given that it is rotating about the z-axis at 6,000 rpm. So we can use that to find our angle. So let's just first convert this into radians per second. So 6,000 revs per minute, if we use dimensional analysis, sorry, it's kind of bad, but if I write the 6,000 revs per minute will simply be 1 rev is just equal to 2 pi rad. And then we know that 60 seconds is equal to 1 minute. And if this is confusing, you can simply just look at the units. They all cancel out. Rev cancels out. A minute also cancels out. So all we're left with is rads per second. So if you type this in your calculator, you'll simply get 628.3 rads per second. And this is simply going to be our rotational speed or angular velocity. And I will just simply call this omega. So if we wanted to find the angle, we simply just have to multiply this by t to get our angle. That means the angle in between the B vector and A vector will simply just be omega times t. So I'm going to just write the flux over here. If our B is simply just going to be 0.15 sine 20 t. So I'm simply just going to plug that in. 0.15 times sine 20 t times the area times cosine omega t. I would simply just plug in the A later. And it's vectorless because dot product. So now let's just find the V EMF. So now I'm simply just going to find the induced voltage or EMF by using this equation as always. So we know what the flux is. So I'm just going to plug it in here. So this will simply just be negative n d over dt times 0.15 sine 20t times A cosine phi t. And I'll simply just plug it in from what we got. So just to make our life easier, I'm just going to take out our constants, which is going to be 0.15, and A, since these numbers don't change. So, rewriting it, we will get negative n times A times 0.15 and d over dt of what's left, sine 20t and cosine omega t. Now, since we are just deriving with respect to t, that means we just simply have to just take the product rule. So, that means this will just be equal to negative NA will still be the same, everything that's out here will be the same. That's an A. And let's take the derivative of sine 20t first, which will simply just be 20 cosine 20t. And we just multiply it by this, and we don't change it at all. Now, taking the derivative of this cosine will give us negative phi sine phi t, which means it will be minus phi sine 20t times sine phi t. So again, this is just derived from taking the derivative of cosine, which is negative phi sine phi t, and then we just left the sine 20t alone. So now we know that this is our V EMF. That means our I induced can be solved with this formula. I induced is simply V EMF divided by the overall resistance. So I'm just going to plug all of this into this formula. And I guess let's just first solve our R first. So what is our total resistance? Well, it is given that the resistivity of the wire is 0.1 ohms per centimeters. So if we have a rectangular loop, which is what was drawn in the image, and we have some length and width, and in this case our width is 2 centimeters and our length is 3 centimeters, and this will also be our width and this will also be our length. Then we also know that we have n amount of turns. So imagine this is just a rectangular conducting loop with 20 turns. So all that means is for one loop, we know that the total resistivity will simply be 2L and 2W for one conducting loop. So 2L plus 2W. Then we also need to take into account of the amount of loops, which is 20, but I will just leave it as N. And this times the resistivity which is given will give us the total resistance, or R. So again, we simply know that we have 2 lengths, 2 widths, and we have n amount of loops. And that will give us our total length, and if we multiply that with the resistivity, we will get the total resistance. And you can just write this as 2L plus W times N times the resistivity. So I'm just going to use a new piece of paper. So again, I induced is just equal to V EMF divided by R. So plugging in our VMF, which what we got is over here, I'm just going to plug it in. We're simply just going to get negative N times A times 0.15, 20 cosine 20t times cosine phi t minus phi sine 20t times sine phi t. And again, I simply just copied what we figured out at first. Divided by the total resistance, which is P N times 2 times L plus W. And again, this is just figured out at first when we found the total resistance. I simply just move rho N to the front. So, just to make our lives a little bit easier, we can try simplifying this. You know that this n will cancel out and this n will cancel out. And we will just be left with the negative sign, negative a times 0.15, and all of this inside. All right, 20 cosine 20t cosine phi t minus phi sine 20t times sine phi t, and all of that divided by rho times 2 times L plus W. So now that we have this, we're able to find our I induced. And if you remember the question, it is asking for when the ring is on the XZ plane or at time is equal to 0. So you can analyze this in two ways. The way I'm going to do is I'm simply just going to plug in t is equal to 0 in here and see what we get. What's simply going to happen when we plug in t is equal to 0 is we're just going to be left with this part, because sine of 0 is simply just going to be 0. So we will get negative a times 0.15 times 20 cosine of 0 cosine of 0 minus phi sine of 0 times sine of 0 over p times 2 times L plus W. And this will simply just go away, because sine of 0 is 0. So we will just get negative a times 0.15 times 20 cosine of 0 is 1 times cosine of 0 is also 1. All that divided by rho times 2 times L plus W. Now we simply just plug in our numbers after we get our equation. So negative times the length, which is 3 centimeters or 0.03 meters, times the width, which is 0.02, times 0.15 times 20, divided by the rho, which is given as 0.1, times 2, and then times the length, which is 0.03 plus 0.02. So after plugging in this into your calculator, you will get 0.18. So this will simply be equal to 0.18 amps. And this is our induced current. So we know that I induced is just equal to 0.18. But what is the direction? Well, the direction can be found by analyzing each contribution. So our first contribution that we can analyze is the B field, which is equal to y hat 0.15 sine 20t. And since sine is initially raising or getting larger, then that just means that our B field is getting stronger. So, according to Lenz's law, or Faraday's law, our induced B will go in the opposite direction due to this contribution because the system will not want more flux. So, induced B, we know, will be in the opposite direction. So if I redraw the picture for you, if we have our x and z axes, that means our y is going into the paper. And if this is our loop, I simply just redrew this picture. We're getting a front view of it. Then that just means that if we know our B field is going into the paper, then that means that our induced B field will be going out. So that means we will have a current that's going this way, or counterclockwise. So this contribution will give us a counterclockwise induced current. So now let's just look at the second contribution, or when this plane is rotating about the z-axis. Well, if we know that flux will get less and less as this rotates, because there will be an angle. So there will be less flux, which means the induced B field will be in the same direction. So if you know that, again, using this diagram, that means that to get a B field in the same direction, we'll have an induced current going this way, or clockwise. So we analyzed the two contributions and we realized that we're getting two different currents two different direction currents. So how do we determine which one to pick? Well, as discussed in EE140, one way you can look at it is by realizing that sine is a faster changing function, which means that counterclockwise will be our answer. But another way you can also look at it is to just look at our, sorry about this, when we took the derivative, you will realize immediately that when we plugged in t is equal to 0, which was in this case, you will realize that this sine portion goes away. And you should remember this sine portion came from the revolutions, the rectangular loop revolving. This was derived from the cosine phi t, or if you want to look at it that way. And all you're left with is this part, which came from the B field, or the sine 20t. So sorry if that was a little bit confusing, but the way you can look at it is you realize that after you take the derivative of the B field and the flux and the revolving, you will realize that this revolving will just go to 0, And all that's left is this B field contribution. So you know that the answer is counterclockwise, or going this direction. That means the current will be going this way. Or looking back at this picture, will be going this way.